Well, here we are in the next topic, Unit 5, what's called the Laplace transform. And this is not just a neat thing, this is sometimes a necessary thing, because like for example, in second order models for spring mass systems or maybe series electrical circuits, the right hand side of these equations, that's the f of t or the e of t in this, and you may see this familiarly from a physics class you may or may not have taken, but it should be relatively similar to any, as you can see, second order linear differential equation. This one with constant coefficients, this one I'm not sure about the 1 over c, but I believe those would be constant coefficients as well. But the e of t or the f of t might be some driving function that's like it's 0 all the time, but then suddenly it's 1 for a short period of time and then it's 0 again. Or this is what's called a sawtooth. It goes from 0 to 1, 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 just like alternating current does, or something similar to that. Or maybe an electric or an electronic piece of equipment warms up to a certain point, and then it cools off to 0 because of an automatic shut off, and then it warms up and then cools off, and then warms up and cools off, and warms up and cools off, creating what this would be called a sawtooth wave. So if this function is one of these animals, even though despite the fact they're functions, we have no way of solving this. You know, what are you going to do? Try to use something like undetermined coefficients? Why do you use undetermined coefficients on a function like that? Piecewise defined. So anyway, we have no direct way of doing that. There is a way to solve problems like that, though, using what's called the Laplace transform. And it solves the other ones too. It's been suggested to me in the past that we leave out other methods and just focus on Laplace transform, but I feel like I wasn't doing justice to the syllabus if I did that. So the problems can be solved by what are called transform methods. We're going to focus on the Laplace transform method. The website from MIT has a pretty good explanation of why this was thought up and why it works. But I don't know if you need that as much as just needs an overview. Exactly what do we do? Well, here's what we do. We have a differential equation in the calculus domain. That's the turquoise color. We're in the calculus domain then. And what we do, we transform this differential equation with what's called the Laplace transform. And I would really like to be able to have a fancy script L in my math work areas, but I can't. So I just have to use regular L when I type this. But Laplace transform of a function turns it into an algebra equation. And then we do some algebraic manipulations with that equation, often using what are called partial fractions. Partial fraction decomposition would be a good skill to have at this point. And then we solve our algebra problem. And then we use what's called the inverse transform. After solving this algebra problem, then we inverse transform to the calculus problem solved. The differential equation problem is solved. And that's even when the function is one of these bizarre animals here, like this. So hence, very useful in physics. I'm sure if those of you that will be taking physics will see that. And it'll make solving this kind of differential equation very nice. Yes, it will make it excellent.
Heavens to Betsy.
Yes, you won't mind it at all. Anyway, they can also solve ordinary differential equations, and in the last lesson you'll see systems of equations. So a good question would be, what is a Laplace transform? And before we move to the next video, let's see what is a Laplace transform. Laplace transform. If f is a function defined for t greater than or equal to 0, the Laplace transform of f of t, denoted, and this is all I can do, I'd really like to use a script L, but I can't, is defined as the Laplace transform of f of t is the integral, that's the improper integral from 0 to infinity, t going from 0 to t at infinity, of e to the negative st f of t dt, provided that that improper integral converges. You may recall, if it doesn't converge, then it diverges, and we have no such thing as the Laplace transform because it's going to infinity. But note that it will be a function of s, because we're going to replace all our t's with numbers, and s will be the only variable in that function. So the Laplace transform of some function of t is a function of s, and that's the algebra function refer to in this picture that we're going to wind up working with. So note the familiar idea of capitalizing. This is f of s with a capital F as an antiderivative, and this is the function itself without being capitalized. But it's a different function from this one, right? But the capital F does show that, yes, we have done an integral there. Okay, before we move to the next video, let's move to the next video before we do any examples. That'll be good.